So good evening, everyone. Today I'll be presenting this theorem by Bochner, which characterizes characteristic functions from R to C. Now the theorem goes like this, that if you have a function phi of t from the real numbers to the complex numbers, and phi is continuous at t equal to 0, and we also need this condition that phi of 0 is normalized, that is phi of 0 is 1, then phi is actually the characteristic function of some probability distribution. Actually, I forgot to mention one condition, which is very important, that phi of t should also be a positive definite function. And phi of t is positive definite, then phi is a characteristic function. Now, before we start, I'll define what a characteristic function is. I'll define what a positive definite function is. So suppose phi is some function from R to C.
I don't need to see it.
Okay. Phi R to C is a function. Then we call that phi is a positive definite function if given some n real numbers t1 up to tn, the matrix formed by the ijth entry phi of ti minus tj, this matrix is positive. If this condition holds, then we call that the function is positive definite. If this holds for all n real points t1 up to tn. Now, if we have some characteristic function, then we know that it's this is some integral of e to the I tx of some probability distribution. Now this function phi of t is, as you can clearly see, this is continuous. Now phi of 0, which we put, is the integral of d of fx. This is normalized because it's a characteristic function, and we'll show that this is also positive definite. So Bochner theorem is actually the converse of the statement that these three conditions are also sufficient to give you a characteristic function. Now, to see why phi of t is positive definite, suppose we consider this quantity. Now we have to show this is greater than 0. We are summing over I and j for points t1 up to tn and z1 up to zn. This is a vector, and when we multiply, what positive definiteness means is this matrix is positive definite, and so when you multiply it by a vector and the transpose, that should be greater than equal to 0. So we can easily see why this should be true, because this will become integral of I ti x e to the I tjx tfx, and we'll have zi zj summation over ij. Now, since this is a finite summation, we can put it inside the integral, And we break this into two parts, e to the I tix zj bar over I and summation zj bar e to the negative I tjx. So this is in fact equal to the mod of e tix mod square d of fx, which is greater than equal to 0. So we have shown that in given a characteristic function, it's positive definite, it's normalized at 0, and it's continuous. Now let us look at the theorem we had written again. So it says that phi of t from R to C is a function, phi is continuous, phi t is positive definite, phi is continuous at t equal to 0. Now if you see the theorem, it at various places, they say they'll mention the condition that phi is continuous, whereas we have just written phi is continuous at t equal to 0. We'll show that both these conditions are equivalent now. For that, so proof of the theorem. We start out by observing certain properties of the of a positive definite function. Suppose phi of t is positive definite, then phi of t e to the power ita is also positive definite, because we consider again the same thing. We want to show this is greater than 0. Now, if we write this as e to the negative I tj times zj bar, then you observe that since phi is positive, we can take these to be some, say, wi's. So this is wj bar. So this is just wi phi ti minus tj wj bar, which is greater than equal to 0 because phi is positive definite. Second, we observe that if phi 1 and phi 2 are two given positive definite functions, and c1 comma c2 are two numbers, real numbers greater than 0, then c1 phi 1 t plus c2 phi 2 t, this is also positive definite. This is easy to see because it's just linearity. Third property we observe is phi of t is phi of t bar, and phi of t mod square is less than equal to 1. Now the first of these properties, this one, it's easy to see because a positive function, positive matrix is also Hermitian. So phi of negative t is phi of t. This is just taking one of t1, this is taking 2 points where we take the first point as t and the second point as 0. This matrix is Hermitian, so this gives you this condition. For the second one, we again take the same points and we construct this. This is the matrix we need to consider. Phi of t, phi of negative t, but phi of negative t is phi of t bar. So this matrix should be positive by the definition of positive definiteness of the function. This means the determinant of this matrix should be greater than or equal to 0. Taking the determinant, we get that this is positive definite because this is just the matrix formed by the points t1 equal to t and t2 equal to 0. So at the diagonal, yeah. So this determinant should be greater than equal to 0, which gives you that mod phi t square is less than equal to 1. Now we observe the fourth very crucial property, that if we have phi as a positive definite function, then it satisfies this following inequality. This can be observed by looking at the function and taking the points t1 equal to t, t2 equal to s, and t3 equal to 0. This will give you the following matrix. In the diagonal, we'll just have ones because we'll have phi of zeros, which will be 1. Or let me just write phi of zeros. I think 1 is better. Here we'll have the following coefficients, which is t minus s. Here we'll have t minus 0, which is t, s minus 0, which is s, and the conjugates of these. Again, because this matrix is positive definite, the determinant is greater than 0. And when you'll expand this is some algebra, you'll get the following. Phi of s minus phi of t mod square is less than equal to 1 minus phi of s minus t mod square plus 2 times 1 minus phi of t minus s. Yeah. This is the following thing we'll get after expanding this determinant, which will equal, we just factorize this term and then we'll take this out as common. Yeah. 2 plus 1 plus phi of s minus t. This will give us, taking the mods, this is the mod, by the triangle inequality, we'll use that this is less than 4 times 1 minus phi s minus t. So we have established this following inequality. In our case, phi of 0 is 1, so we get the correct inequality. From here, you can observe that since phi is continuous at t equal to 0, if we take s minus t as mod s minus t less than delta, that is s minus t is very close to 0, then we can make this arbitrarily small. And from there, the phi of s minus phi of t is arbitrarily small. So we get that phi of s minus phi of t is actually continuous everywhere. So you can see that the positive definiteness of a function is quite a strong condition, because we prove that if a positive definite function is continuous at t equal to 0, it's actually continuous everywhere. In fact, it's also uniformly continuous because this boundary doesn't depend on what t you're taking. So we have reduced this problem to solving, proving that if phi of t is positive and continuous everywhere and normalized, then phi is a characteristic function. Now, we'll put the following assumption on our function phi of t and prove that this is the characteristic function of some probability distribution in this case. And then we'll do the general case after this using this particular result. So assume that phi of t is absolutely integrable. Now consider the following function of x, 1 over 2 pi. Now, considering this function, you can see how we can get phi of t as some okay. Okay, so there was some slight technical issue, but here we were proving that if phi of t is absolutely integrable, then phi of t and the above conditions are already there. In addition to that, phi of t is absolutely integrable, then phi of t is the characteristic function of some. So we can consider the following function, f of x is equal to this quantity. Then there's a natural way in which phi of t will come out as the uh, characteristic function of a distribution whose density is actually f of x. So first we'll prove that f of x actually behaves like a density. So we'll prove that f of x is greater than equal to 0 for all x, and integral f of x is integrable, and its integral is 1. So starting off with the first claim, which is non-negativity, we write f of x in this form. Now this is equal to the previous one because this given function monotonically increases towards e to the I minus I tx phi of t. So by the monotone converges theorem, this converges to the above this function. Now we claim that this is actually equal to limit t tends to 0, 1 over 2 pi t. T minus x. So first of all, we are converting it into this form so that we could use the positive definiteness of the function. Now, why this is true is because we start off with this. This is just a change of variable. Now assume u to be t minus s and v to be t plus s. This will give, now first looking at the bound for u can vary between minus t to t, because t varies from 0 to t and s varies from 0 to t, and we are not looking at v right now. So u can vary from minus t to t. Now v can actually vary from 2t minus mod u to mod u. This is easy to see. Now using the change of variable and calculating the determinant for we are putting u and v as t minus s and t plus s. So t will be v plus u by 2 and s will be v minus u by 2. Now you can form the matrix by the partial derivatives, the Jacobian matrix, and you can take the determinant, which will be half. So by the change of variables formula, this will be equal to minus t to t, the above integral is equal to minus t to t mod u to t minus mod u, the factor half, which comes from the Jacobian. Now all the functions are functions of variable u. So we integrate over v to get the following. This is equal to integral minus t to t minus mod u, t minus mod u e to the iux phi of u du. Like when you integrate over v, you'll get 2t minus 2 mod u. And when you'll divide it by 2, you'll get t minus u. This is taking out the t, you'll get. Now we just change the variable to t, which was being used earlier. So you'll see that this integral is actually equal to that. So it's just a change of variable. So we have proved that that is actually equal to this. Now we have to prove that this function is actually non-negative. For this, we'll use the Riemann sum approximation for this function and prove that the Riemann sums are always non-negative, and hence this this is the limit of the Riemann sums, so that will be non-negative. For that, what you do is you partition, you have 0 to t here and 0 to t here. You partition into n intervals of equal length and choose the point ti is on t1, t2, ti is on this side, and similarly partition this side, the s side. This is the t side, this is the s side. The s side into n partitions, and the overall partition will be given by the product of these partitions. Here also you partition them into n equal intervals, choose SIs, and we are choosing SIs in such a way that SI is equal to TI for all I from 1 to n. This will give us the value of the Riemann sum as e to the negative I ti minus si x actually no. It's not working. Yeah, it's working. Okay.
If you touch it, it's enough. Actually, it'll go. You don't need to erase it.
Okay, okay. So this the Riemann sum of we'll calculate the Riemann sum by taking the value of the function at ti in the partition in this particular partition at ith and jth place. We take the value of the function at the point ti sj comma ti. So this will give you the value of the Riemann sum as negative I ti minus sj x phi of ti minus sj. Now delta t, this will be delta some delta L squared, because the partitions are of equal length, so these are squares. We have to prove this is greater than 0. We can forget about the delta L square term as it is positive and it's the same overall terms of this quantity. So we look at tix phi of ti. Now we can write sj as tj because we had chosen sj's in such a form. So this is just tj x summation. Now this is by the definition of positive definiteness of phi. We are just choosing these points. This is the bar of. So we are choosing these points, and by the positive definiteness of the matrix, this is greater than or equal to 0. Now, when we do this over all partitions, we make the partitions of this square 0 comma t cross 0 comma t finer and finer with more n. So this sum will go towards the Riemann integral, as this function is Riemann integrable. So this is greater than 0. So we get that f of x is greater than or equal to 0 for all x. Now we want to prove that f of x is in fact integrable, and we also want to prove that phi is the characteristic function of some distribution. For that, define the following new quantity. Now our rationale for choosing these functions is that these functions f sigma of x actually monotonically decrease towards f of x as we go towards 0. So we can use the monotone convergence theorems, and we'll use it in the following way. First of all, we have seen the definition of f sigma x. So we calculate the quantity, the Fourier transform of f sigma x. Now this will be in fact expanding f sigma will result in we expand f of x, we get a factor of 1 by 2 pi from the definition of f of x. So we take that out. Now we since these functions are continuous, we can use Fubini's theorem here, and we can just change the order of the integral, and this will be equal to the following double integral. ds dx. Now what we do is we want to integrate this over x. We want to integrate this out over x. Sorry. Phi of s. Now we look at this quantity and we complete the square as follows. X is here, so completing the square, we get that the quantity in the exponential, this is actually equal to, because we have two minus signs. So this is minus of t minus s by 2 sigma squared. Now this quantity in the integral, we have written it like this. This is a complete square, and this quantity doesn't depend on x. So we can take this out. So I'll just box this because, yeah, and just use this here to get the following. Phi of s e to the exponential of negative t minus s squared by 2 sigma squared. And the second integral here, the integral inside this over x will be changed in this form. We take sigma squared by 2 out. You'll get the following integral. Now observe this, that this is just the Gaussian integral. Just it is shifted by this particular factor, and it's multiplied by this minus sigma squared by 2. So this will actually integrate over, if we change the variables, this will integrate out to square root of 2 pi by sigma. Putting this value there, we'll get that 1 over 2 pi, we'll get the following quantity. Exponential of minus t minus s squared by 2 sigma squared ds, and we multiply square root 2 pi by sigma here. We cancel out, so this will become 1 upon square root 2 pi sigma integral minus infinity to infinity phi of x ds. So we have got this particular quantity. Now here we just put t equal to 0. Okay.
Make sure that you won't leave them.
Yeah. So for t equal to 0, we'll get that this quantity is actually equal to integral of f psi sigma, because we had started with the Fourier transform of f sigma x, and putting t equal to 0, you'll get this integral. This is equal to 1 over 2 pi sigma of exp t0, so s squared by 2 sigma squared ds. Now since the this is actually less than or equal to 1, because f sigma x are all positive, we have shown that they are non-negative, and mod of phi of s, exponential of whatever here is, this is less than equal to exponential of whatever here is. They are positive quantities, phi is less than, always less than equal to 1. So when you integrate this over the given block, you'll get the